Okay, I want to take another look at the Atwood machine. I'm going to show you a little trick we use in dynamics, ME242. So if you take that with me, I will show you lots how to work with pulleys. And the trick is that these two things are moving with relative motion. If one goes up an inch, the other goes down an inch, and we're going to use that fact. And the reason I want to show you this is because the solutions in our book and the ones we see without knowing this thing called a datum, we'll call it a datum. Without using the datum, we have to either draw our free bodies normal, like over here and right here, but then they go in here and say, well, we have to assume the acceleration direction. We have to assume that A1 is in the opposite direction of A2. We don't have to assume that, and let me show you. So let's redraw this problem. We got a pulley, we have some mass 1, we have some mass 2, and if we look at the free body diagrams on both, we get the same forces. We have a tension, we'll call it T1, and we have some M1 times the acceleration due to gravity going down. We can do the free body diagram on 2, so this is on 1. On 2, we also have the component of weight going down for mass 2, and we also have some T2. Now we do know one trick. We can say T1 is equal to T2 and just call it T, and that's because the tension in a pulley configuration, a tension in any single line is the same. So it doesn't matter if it's wrapped around a pulley or not, the tension provided by that single line is the same. Now if you have two ropes in your system, then each one may have a different tension. Okay, so what I want to show you is the datum. It's a reference point. We'll call it right through the middle of the pulley, because we can ignore this top of the pulley right there. What this does is gives us a place to measure. I'm going to measure down to mass 1 and call that minus S1. And we can get rid of the minus and just call it the distance S1. And down to M2, we get a distance S2. Now here's the trick. I will say we can add up all of this string length right here and get relationships between the motion by doing so. So let's do it. If I say the total length of the string and then just start adding it up, I'm going to get, if this is some y is equal to 0, we'll call this a minus S1 right here. And then when we add up this piece, we get a minus S2. We can actually add this piece in here too. We'll call that, it can be positive or minus. We'll call it positive. We'll call it SAB. This part is always constant. So is the total length. The total length is always constant of the string. Think about it. It's not stretching. As one goes up, the other goes down. So we can say that is a constant value. Now the trick comes now by using that constant, or the fact that the length is constant, by taking the derivative of this with respect to time. So when I take the derivative of a constant, which this is constant and this is constant, I get a 0. But for the position S1, that turns into a minus V1. Position S2 turns into a V2. And once again, since this was constant, derivative of a constant with respect to time is 0. So this just gave us a relationship that the velocity of 1 is equal but opposite to the velocity of 2. That's very, very useful. And we can go one step further and get our relationship for the acceleration. The acceleration is equal but opposite to the acceleration of 2. Alright, let's look at 1 again and take the forces that we just drew. I have a T going up, a minus m1g going down, and that equals m1 times the acceleration of 1. We also have this other tension going up, and remember we said that they're all equal, and I replaced it just with a T. We have a m2g pointed down, and then an m2a2. Now, the problems in our textbook will typically say, well, look, they're saying the acceleration is that way. They're assuming it. I don't know. Yes, intuition has built your brain up to the point where you know that when one goes up, the other goes down, and that they're going to have equal but opposite accelerations. But what if we got a different pulley configuration? What if we had something like this, where it's attached to the ceiling and then had a mass here and a mass here? Then we really need the datum. So we'll do lots of problems like that in dynamics, but I wanted to show you where the good solution, or one of the good solutions for this comes from. Now we have the forces on 1 and on 2 and the accelerations all, let's call these equation 1 and 2, and we can use this last relationship, A1 is equal to minus A2. Call that equation 3. Solve these the three equations any which way you want. You will end up with the solution that we take the difference of the mass on top and add the masses up and put that in the denominator. All of that's multiplied by g. So there's your Atwood machine. Now the datum would still also work if we had a problem like this, where maybe we had a mass and another mass and a pulley like this connecting the two. I would draw my datum here and make a different color. Let's say my datum is here, and then we could ignore that constant value that goes over the top of the pulley, and then I would measure this as some S1 and this as some S2. The main use for this is for more difficult pulley configurations, but we can use that to get a good proper solution for the Atwood machine. We're kicking off even more forces now in this unit for this next test. I just wanted to bring this to your attention, and the next thing we're going to talk about is the other forces we haven't introduced, like the forces of friction and spring forces.